All right, at the start of today's class, just there's an announcement in here for you guys to look at. This is for the American Society for Biochemistry and Molecular Biology. They have a meeting next week. I did not know that this society existed, so maybe they're new, but nonetheless, it could be interesting to some of you, so please check it out. And then a couple reminders about this week. Thursday of this week, which is the 2nd, I won't be around, so there won't be office hours that day. And you will have a substitute in here during the normal class time, so Professor Larson will be teaching in my place that day. There is going to be a recorded lecture. I recorded it yesterday and have it scheduled to release on YouTube. I've never used the scheduled release function before, so hopefully it works, but I'll check on it anyway. So that's going to release right around the time that class would start, and then the notes are already posted so that you'll have access to those. So that's just for continuity. I don't know if Professor Larson is going to do exactly the same thing that I would have done, but it'll be still useful for you, so I encourage you to come. All right, but we do have to make sure we get through everything today because Thursday's lecture is already recorded and contingent upon us getting through today's material, so I can't dilly-dally. I have to get into it. As is tradition on Tuesday, we'll start with some information reminders about work habits. And so let's look at how we did on the first. This is technically the second homework assignment, but the first one that deals with the actual textbook material that we've been covering, Chapter 1 homework. So the average score was good. I don't really care too much about the homework scores, it turns out, because that's not really indicative of what you're learning necessarily. So, but it was quite high. 11.49 out of 12 was the average score for everybody. One thing to keep in mind with the homework scores, if you're obsessing about getting every point, is that functionally speaking, in terms of how it affects your final grade, an 11 out of 12 and a 12 out of 12, there's really no difference between them on a homework assignment, because 11 out of 12, if you get 11 out of 12 on every assignment, you'll get 5.5% of your homework grade, but we always round up to the next highest grade if you're above 0.5 anyway. So as long as you get 11 out of 12, you're not going to benefit your grade anymore if you get 12 out of 12. So that's something to keep in mind if you're worried about the scores that you're getting. So don't obsess over the scores too much. And again, we drop your two lowest also, which helps a little bit. Now, the part that I would like to see some improvement in is how many attempts we're doing on the homework assignment. So the average student in this section did 2.87 attempts out of 4 possible. And the number of students that did all 4 attempts was just over 50%. So a little bit better than the review assignment, but still not where I'd like it to be. I'll mention this too many times that you guys will get sick of it, but doing all 4 attempts on the homework is sort of a good indicator that you're putting in the effort that's required. So I have statistics on Blackboard in one of the documents there, which I'll probably show in class at some point to make sure everybody sees them, which shows that the students that do all 4 homework attempts every week have significantly better outcomes in the course. And that's not the only thing you can do, but that at a minimum indicates that you're performing at the appropriate level. And if you're not doing that, then that usually means that you're not quite doing what is necessary to succeed on the exams at the level that you would like. So I'm going to keep reminding you of that over and over again, and this is the first indication that we still have some work to do in that regard. But let's get into the material today, because as I said, we have to get through everything. So last time we learned about quantum numbers and orbitals and subshells and shells and all those things. And so we'll start with a couple of example problems related to that, just to remind us of some of the things we learned. But what we're going towards today is how to figure out in an atom how many electrons go into each of those shells, subshells, and orbitals. So how do we divide up the electrons into the different subshells and orbitals that we have available? So that's what we're getting to today. But first, let's review some of the basics that we learned last time. So this question here, what is the smallest principal quantum number that has d orbitals? So for this one, we're working a little bit backwards in terms of the rules that we learned for quantum numbers. So we're giving you here that it's d orbitals, meaning it's part of a d subshell. And just remember that these letters here that we associate with subshells or orbitals correspond to the second quantum number L. So you have to remember these 4 here especially. L can be 0, 1, 2, 3, 4, and so on. The first 4, 0, 1, 2, 3 are the ones that we're going to encounter all the time, because those are the ones that would appear in the subshells that are filled on the elements in the periodic table. So these correspond to different letters. So 0 is S, 1 is P, D, F, and then after that is alphabetical. But as I said, it's really these 4 here that we need to worry about. So in this problem here, we're telling you that it has d orbitals, which means that L equals 2. And we're looking for the smallest principal quantum number where that can be a possibility. So principal quantum number is the first one, n. All right, so that's what we're looking for here is n. Remember that the rules are that L starts at 0, and the possible values of L go all the way to n minus 1. So if L equals 2, that means n minus 1 has to be greater than or equal to 2, which means n has to be greater than or equal to 3. All right, so 3 would be the answer for this one. That's the smallest value of n where it's possible to have d orbitals, because if n equals 3, L could be 2, but if n is anything smaller than 3, if it's 1 or 2, you can't have L equals 2. So again, knowing those rules for the relationships between NL and M sub L, the three we learned last time, will help you on problems like this. Any questions on that one quickly? Okay, and then this one is very similar to some things we talked about last time, but just remind ourselves. So how many orbitals have the following quantum numbers, NL equals 6 and 6? So when you're doing a problem like this, there's two things you want to think about. There are relationships that we talked about, number of orbitals in a shell. So, but you don't want to blindly apply these. There's one thing we need to think about first. But we'll give these relationships here, which will be useful in a lot of these problems. Number of orbitals in a subshell, we also talked about. And for that, it depends on L. And it's given by 2L plus 1. So for this problem here, you might just be like, well, okay, L equals 6, 2L plus 1 equals 13, done. But there's one thing you need to think about first, which is this even an allowed combination of quantum numbers to begin with? Okay, so if n equals 6, the possible values of L are going to be 0, 1, 2, 3, 4, and 5. Remember, the biggest value of L is n minus 1. So it's not possible to have n and L both equal to 6. This is not an allowed combination here. And so that means there would be 0 orbitals that have those quantum numbers. So that pair of n and L values is not an allowed combination of n and L. If n equals 6, then L cannot be any bigger than 5. Or if L equals 6, n has to be at least 7. So none of those two don't work together. So not an allowed combination of quantum numbers. So there would be 0 orbitals that have, put 0 in parentheses so that that's not an O, 0 orbitals that would have those sets of quantum numbers. It's not an allowed combination. So when you're doing problems like that, first also think about, are the quantum numbers that we're giving you even a valid set? If they're not valid set, if they violate one of the rules for quantum numbers, then there would be 0 orbitals or 0 electrons that would have those quantum numbers associated with them. It's just not possible. All right, so any questions on that? So you would use these relationships if this was an allowed pair, but in that case it would be 2L plus 1, but since you're not an allowed pair, then the answer is just 0. You don't have to do that. All right, and then finally the last set of sample questions that are representative of things you might see on homework assignments and tests. Which of the following orbital designations is incorrect? So this kind of is a similar one to the last one, where you have to think about which of these pairs of quantum numbers are allowed and then do they correspond correctly to the letter designation that's provided. All right, so we have to, again, keep in mind the SPDF L equals 0, 1, 2, 3 convention to make sure that we match those up properly. So for this first one here, n equals 2. If n equals 2, L can be either 0 or 1, so that value of L is okay. And when L equals 0, that corresponds to an s orbital. So this one is fine. For choice B, n equals 3, that means L is 0, 1, or 2. It goes to n minus 1. As a reminder of that, L goes to 0 to n minus 1 are the possible values. So L equals 1 is fine. When L equals 1, that's a p orbital, so 3p is correct for that. And then when n equals 4, L equals 2, is that an allowed combination? N equals 4 can have L equals 0, 1, 2, or 3. Any of those possibilities is fine. So this combination works. And when L equals 2, that's a d orbital, so that's fine. So by elimination, it should be the last one is the incorrect one. And what we see is sort of the same problem that we had in the last example, which is that n equals 3, L equals 3. If n equals 3, the largest value of L would be 2. It has to be 0, 1, or 2. So this value of L does not go with that value of n. It's not possible to have those two together. So that one would be the one that's correct. 3F would be correct if that was an allowed combination, because L equals 3 does correspond to F, but you can't have 3F. You can only have 4F, 5F, 6F, anything bigger than 3, because L equals 3 needs n equal to 4 or higher. All right, so again, just reiterating the rules. And then the last type of problem that we might have to deal with, and one of the concepts we talked about, are the shapes of atomic orbitals. Now, just to remind you, when we say the shape of an orbital, they don't have specific defined regions, or it's not telling you that the electron moves in a certain path or is exactly in a certain place, but this is the region in space where the electron is most likely to be found. It's a 90% probability is usually how it's defined, so it's going to be where is that electron likely to be if it's in that orbital, but it could be anywhere inside of that surface 90% of the time, so it's not fixed in one location or not moving in a regular path. So when we want to identify orbitals, we first think about there's 3 major types that we expect you to know, S, P, and D. F orbitals are way more complicated, so we don't really give those as examples in this course. So S orbitals are spheres, P orbitals are figure 8 shaped, and most of the D orbitals are sort of 4-leaf clover shaped. All right, so clearly this is a D orbital. It has those 4 lobes in it, so we can eliminate choice A, because it can't be a p orbital, and pxy is not a real orbital anyway. The p orbitals are just px, py, or pz. But which of these d orbitals is it? So for that, we have to look at how it's oriented in space. And what you can see here is that the lobes are along the x and y axes here. So the ones that are shaded go in the positive and negative y directions. The unshaded one goes in positive x and negative x. So that tells us it's in the xy plane. So that eliminates dz squared. Dz squared is the one that has the odd shape that looks more like this. It has the donut around it. So if you see the donut, that's dz squared, but this one clearly doesn't have a donut around it, so it's not dz squared, it's not in the z direction either. So it's one of these two. These two are probably the 2 hardest to distinguish from each other. We have to remember that the ones that are labeled as Cartesian planes, x, y, x, z, y, z, those have the lobes in between those respective axes. All right, but what we can see here is that the lobes of this orbital are directly along the y-axis, directly along the x-axis, they're not in between the two. So that means it has to be dx squared minus y squared. That's the one where it's a 4-leaf clover shape, but you have lobes in the right along the x and y-axis, not in between. dxy would look something like this, where if this is the x and y axis, dxy would be in between like that. So those are the 2 that are the most similar to each other. They're both in the xy plane, and they just differ by 45-degree rotation. But this would be dxy, where it's in between the x and y axis, but when it's along x and y, that's x squared minus y squared. So the d orbitals are the toughest ones, but there's only 5 of them, and the name kind of gives you some hint about the orientation of it, so that's helpful to look at. All right, any questions on either of these 2? All right, so hopefully that reminds us of the things we did last week, especially in the second lecture of last week. And so now we're going to go into what we're learning today, is how to define the quantum numbers for all the electrons in atoms and how to then figure out which shells, which subshells, which orbitals have electrons in them and how many electrons there are. So it's called Electron Configurations, which is the title today. So in order to do this, we do have to recognize that there actually is a 4th quantum number. So far we've defined 3 of them, n, l, m sub l. As we said, n defines the energy and the size of the orbital. L tells you what type of orbital is, the shape that it is, and m sub l refers to the orientation of that orbital if there are multiple m sub l values for some cases. Okay, so those are the 3 that define an orbital, but there is a 4th one that we need to define the quantum numbers of an individual electron, which is called the spin quantum number. Now, the concept of what spin actually means physically is tough. It is a quantum mechanical parameter, not something that's easy to relate to everyday life. We'll give a little bit of a definition of what it means, but the important part for us is that it only has 2 possible values. It's either plus 1/2 or minus 1/2. So there's only 2 possible values. And so what we call those sort of in spoken form would be if it's m sub s equals plus 1/2, we say that the electron is spin up. And if it's m sub s equals minus 1/2, we say that the electron is spin down. All right, so those are the only 2 possible values for m sub s, and the individual m sub s value of an electron has no bearing on the energy. So if you put an electron into an orbital spin up, or an electron into an orbital spin down, for that single electron, there's no energy difference between spin up and spin down. It has no bearing on the energy. But as we'll see, it is still important to think about sometimes. Now, what does it mean exactly physically? This, again, is the sort of hard one to internalize, but it's a property of the electron itself. So the other three quantum numbers define something about the orbital that the electron is in, but the m sub s value is a property of the electron, not of the orbital. And what it refers to is the direction of its magnetic field. So something that you may have talked about if you've taken physics, probably the second physics course that you would have in your normal sequence here. If you have a moving charge, it generates a magnetic field. And so electrons are moving charges, so they generate magnetic fields. And so that, the z component of that magnetic field can be pointing up or pointing down, and that gives you the different m sub s values of being plus 1/2 or minus 1/2. From a chemistry standpoint, that doesn't really matter, that physical definition, but that's just a little bit about what it is. So with all four quantum numbers together, then, every electron in an atom is going to have a set of four quantum numbers that define it. N, L, and M sub L, those three together tell you which orbital it's in. And then M sub S is the fourth one, which tells you the direction of the spin for that electron, pointing up or pointing down. So those are the four quantum numbers that we can use to define every electron in an atom. Okay? So that's one thing we're going to be able to do then is talk about quantum numbers for every individual electron. We don't always talk about it in those terms, but that is in principle what we're getting towards. And we need some rules then to be able to do that. And so the first rule that we're going to talk about is called the Pauli exclusion principle. Again, scientist Pauli here does not look too thrilled about his world-changing discovery, but nonetheless, it is important in defining the electron configurations of atoms. And so the definition of Pauli exclusion is that no two electrons can have the same four quantum numbers. So if you have a multi-electron atom, more than one electron, every electron in that atom is going to have a unique set of four quantum numbers. Some of them will be the same. It's not that they all have to be different from each other, but there will be a unique set of four for each individual electron. No two can have the same four quantum numbers. Okay? Only need to write that once, sorry. All right, so no two electrons in an atom can have the same four quantum numbers. That's what Pauli exclusion principle means. Now, what is the implication of this for what we're doing in this course? Well, remember that we just said that m sub s has two values, plus 1/2 and minus 1/2. So that means if you're putting electrons into an orbital being defined by the first three quantum numbers, it can either have m sub s equals plus 1/2 or m sub s equals minus 1/2. So the most you can put into one orbital is two electrons, because one of them can be spin up, one of them can be spin down, but you can't have two spin up electrons in the same orbital, or you can't have more than two in total, because that would require you to duplicate a set of quantum numbers. So for us, what it means is that there's a maximum of 2 electrons per orbital. So when we're filling orbitals with electrons, figuring out how many electrons are in each orbital that are available to us, there's no more than 2 electrons per orbital. There could be 0, there could be 1, or there could be 2, but no more than 2. And when an orbital has 2 electrons, so if it's doubly occupied, as we say, the spins have to be opposite. One has to be spin up, one has to be spin down. All right, and as we'll see, you don't always put 2 electrons in an orbital. It depends on how many electrons you have and which orbitals you're talking about. There's other considerations that we'll get to in a little bit. But when you put 2 electrons into the same orbital, the spins are paired, which is what means they're opposite of each other. So one is spin up, one is spin down. Oh good, my pen stopped working. Oh no, not this again. I had this problem a few times last year, and I thought we were past this because it never occurred in the fall semester when I was teaching, where my stylus just stops working and the only solution is to restart my tablet, which is really terrible. Oh gosh, sorry about this. This is not what we needed today when we have specific things we have to get through. Alright, so if you notice that there's a discontinuity in the video, that's because I did stop to rescue my tablet from disaster. So we're back into this, and so what it means is with Pauli exclusion, maximum of 2 electrons per orbital, and when the orbital has 2 electrons, one is going to be m sub s equals plus 1/2, and the second one in that orbital would be m sub s equals minus 1/2. All right, so that's going to be some implications of the Pauli exclusion principle when we start talking about how to arrange electrons into orbitals and also then how to define the quantum numbers for those electrons. All right, and with the Pauli exclusion principle in mind, we can now define some additional relationships that follow from it. So we already talked about in a given shell or a given subshell how many orbitals they are. We use those relationships. We talked about them a little bit earlier today in some of the example problems. So what we learned last time is that in a given shell, which is defined by a value of n, the number of orbitals is going to be equal to n squared. All right, now what we just said, though, from Pauli exclusion principle is that there's a maximum of 2 electrons per orbital, which means that the maximum number of electrons in the subshell would be equal to 2 times that, 2n squared. If you have n squared orbitals in a shell, 2n squared will be the maximum number of electrons you could put into there. It's just at most 2 electrons per orbital. So when n equals 1, there's a maximum of 2 electrons. When n equals 2, there's a maximum of 2 times 2 squared, which is 8 electrons, and so on. So the number of electrons, the maximum number of electrons in a shell is a pretty simple relationship, 2n squared. And then similarly for a subshell, we saw that the number of orbitals available in a subshell depends only on the value of L. It's given as 2L plus 1, where the n and L together define what the subshell is, and then 2L plus 1, though, is the relationship that tells you how many orbitals would be in that subshell. And so what that means then is, as we said, maximum of 2 electrons per orbital. The maximum number of electrons is 2 times 2L plus 1, which you can distribute if you like, but I'll just leave it as 2 times 2L plus 1. All right, so let's just give a quick couple examples of this, of how this works. So if we're in the third shell, which is n equals 3, the maximum number of electrons that we can put into the third shell is 2n squared, which is 2 times 3 squared, which is 18. So the third shell in any atom can have at most 18 electrons in it. And then within the n equals 3 shell, we have 3 possible subshells. So the first subshell is 3s, L equals 0. So the maximum number of electrons in 3s is now 2 times 2L plus 1. L equals 0 for 3s, so 2 times 0 plus 1 is 2. For 3p, L equals 1, max number of electrons is 2 times 1 plus 1, which is 6. And then finally for 3d, which is the third subshell, L equals 2, the max number of electrons is 2, L equals 2, so it's 2 times 2 plus 1, and that's going to be 10. So of those 18 electrons that we have in the n equals 3 third shell, 2 of them can go into the 3s subshell, 6 can go into 3p, and then 10 can go into 3d. So if the third shell is completely filled, all 18 electrons are there, that's how they're going to arrange themselves into the different subshells. But this, again, these are all maximum numbers. You won't necessarily have this number of electrons in every shell or every subshell, but this is the most that you can put in, and it's defined by those quantum numbers as well. All right. Any questions on those concepts? Now, the next thing we need to talk about is when we want to define how the electrons are arranged into subshells, into orbitals, we need to understand the factors that influence the energy of that electron. Because what we're going to be doing is we're going to arrange the electrons into the subshells from the lowest energy subshell up to the highest energy subshell until we've added all the electrons that we have. So we have to understand what factors influence the energy of an orbital or the energy of a subshell, and then the energy of the electron that would be in that. And so that's going to be, there's a couple of factors here that go into it. And so one of them is the proton-electron attraction. So if you have more protons in a nucleus, that leads to a stronger attraction, which correlates with a lower or more negative energy. We can kind of see this from the Bohr equation. Remember the Bohr equation, we have that one only works for hydrogen, as we said, but the concept is still there, and the Bohr equation has that z-squared term that you can include if you have more than one proton in the nucleus, where the more protons you have in the nucleus, the stronger the attraction to the electrons. So that leads to a lowering of the energy of the subshell as you add more protons to the nucleus. So as we go across the periodic table to increasing atomic number, we add more protons to the nucleus, and that tends to cause the subshell energies to get lower because of that stronger attraction. But there's also a second factor that kind of counterbalances this, and really what we're doing is trying to balance these two effects. The other one is when you have more than one electron, you also have electron-electron repulsion. We didn't worry about that for hydrogen because there's only one electron in hydrogen, so it doesn't have any other electrons that it needs to care about. But in any other atom on the periodic table that has two or more electrons, those electrons are going to repel each other also. So in multi-electron atoms, the electrons experience repulsive interactions with other electrons. All right, so attractive interactions are stabilizing, they lower the energy, but repulsive interactions are destabilizing, they raise the energy. So when you have these sorts of electron-electron repulsions, they destabilize the energy of that electron. And so when you're trying to decide how to arrange the electrons in a multi-electron atom, it's sort of a competition between these two effects. You want them to get as close to the nucleus as possible because that increases the attraction to the nucleus and stabilizes them. But on the other hand, if the electrons are smushed too close together, they also start to repel each other more. And so in that sense, you want them to be spread out. So there's really two counterbalancing effects that go into play when determining the relative energies of subshells and how that works in a multi-electron atom. So those are the two major contributions to the energy, the attraction to the nucleus as well as the electron-electron repulsion. And so then what is going to really then determine that, the balancing of those two effects is what's called shielding and penetration. These are both properties of subshells and atoms. All right, so what does shielding refer to? Shielding is an effect that reduces the nuclear charge experienced by an electron. And so what happens here is if you have a multi-electron atom, if you have some that are close to the nucleus and some that are further away, which will usually be the case because, as we said, the different subshells have different average distances from the nucleus. So the ones that are close to the nucleus are going to partially block out that positive charge from the nucleus. They're going to, in some sense, almost partially cancel it out. And that means the electrons that are further away, they don't experience that full positive charge because the electrons on the inside are kind of blocking them from it. So that's what we mean by shielding. So the inner electrons, the ones that are closer to the nucleus, they block the outer electrons from experiencing the full nuclear charge. And so this results in what's called the effective nuclear charge. We're not going to really quantify this, but we should understand a little bit what it means. Effective nuclear charge is the amount of charge that the outer electrons would feel, or that any electron would feel, and it's going to always be smaller than the total nuclear charge because of that partial shielding effect. And particularly for outer electrons, those that are further away from the nucleus, they're blocked by the inner electrons, and that effective nuclear charge is going to be smaller. So in a carbon atom, for example, you have 6 protons in the nucleus, but because of shielding, the ones that are furthest away, the electrons that are furthest away, might only feel the charge of, let's say, 2 or 3 protons. It's not a full effect because of that shielding interaction. So that's what shielding referred to. And then the other one that we need to understand to rank the energies of subshells is penetration. So the n value, the one, the first principal quantum number here, that has an effect on energy just like it does for the hydrogen atoms. So remember, in hydrogen atoms, we said that n equals 1 was lowest in energy, n equals 2, then n equals 3, and then n equals 4. That is still largely true, and it is true in multi-electron atoms, but the difference with multi-electron atoms is that the different subshells within a shell also have different energies from each other. So in hydrogen, 2s and 2p would be identical in energy. It only depends on n for hydrogen. But for anything that has more than one electron, 2s and 2p are different energies, and it turns out that 2s comes before 2p in terms of energies, lower in energy than 2p. So why is that? And that's because of what's called penetration, which is the ability of an orbital or an electron to get close to the nucleus. All right, and so what this does is it reduces the effect of shielding. Because we said that shielding is blocking out some of the nuclear charge, but if you have an electron in an orbital that can get close to the nucleus from time to time, that sort of mitigates that shielding a little bit. So to understand where that comes from, we can think about the radial probability functions that we talked about last time, 4 pi r squared psi squared as a function of the distance from the nucleus r. Again, that's the probability of finding an electron at a certain nucleus. And if we compare 2s to 2p, 2s looks something like this. It has one radial node, n minus L minus 1 is radial nodes that we talked about last time. So the radial probability distribution for 2s looks something like that. Now for 2p, it turns out, so this is your most probable radius. That's the most probable distance from the nucleus for a 2s orbital. So blue is going to be 2s. But then for 2p, which I'll do in red here, it turns out that the peak for 2p is actually a little bit closer than 2s. So the most probable radius for 2p is a broader distribution, and the peak occurs a little bit closer for 2p, which I'll show in red here. But in the 2s radial probability distribution, we have this little region here that's close to the nucleus that has non-zero probability. So even though the peak radius, the most probable radius for 2p is a little bit closer, 2s has this ability to get really close to the nucleus because of its radial probability distribution function, and that leads to it having a lower energy. So the energy of a 2s orbital will be less than the energy of a 2p orbital because of the better penetration of 2s. All right, and so what that means then is that in any subshell where you have the possibility of s, p, d, and or f orbitals, or any shell I should say, the s subshell will be lower in energy than the corresponding p subshell, lower in energy than d, lower in energy than f. So in the n equals 2 shell, you only have s and p, so s is lower than p. When n equals 3, you have sp and d. 3s will be lower than 3p, which will be lower than 3d. And then for, I wrote that wrong again, gosh, that should be f. And then for n equals 4, where you have spd and f, 4s comes before 4p, which comes before 4d. Oh my gosh. All right, hopefully I'm done making mistakes on that. That's what the order should be. SPDF, that's the order they come in, lowest to highest energy for any subshell. Now, not all subshells have all 4 of those, but if they did, that's the order they would come in. And however many there are, that's the relative order from lowest energy to highest energy. So energy increases left to right here, okay? So that's how we're going to then do this, is when we want to fill subshells, fill orbitals in a multi-electron atom, we're going to fill the lowest energy subshells first and then go higher and higher in energy until we add all the electrons that we have for that atom. And then the other thing we need to be aware of, though, when we do that, is that some orbitals are at the same energy as each other. So each individual orbital is not necessarily going to have a unique energy level. Sometimes you have more than one orbital that has the same energy. So that's what we call a degenerate orbital. It doesn't have anything to do with them, breaking the law or anything. That's not what degenerate means in this case. It means they have the same energy. So orbitals that have the same energy are called degenerate. This doesn't come into play too much when it comes to writing out electron configurations in terms of how many electrons are in each subshell, which is how we usually do it. But if you want to fill individual orbitals and say how many electrons does this orbital have, how many electrons does that orbital have, what's the relative spin, understanding a little bit about degeneracy is important here. So which orbitals are degenerate? Well, the orbitals in a given subshell are all degenerate with each other. So it's pretty simple to know which orbitals would be degenerate. Any ones that appear in the same subshell as each other have the same energy. So that means they have the same N and L value. All right, in an S subshell, you only have one orbital, so you don't have degeneracy to worry about. It's just a single orbital. But for any of the other subshells, P, D, or F, you have multiple orbitals present, and all of those orbitals in a single subshell would be at the same energy as each other. So the simplest example that would have this is the 2p subshell. L equals 1, so 2 times 1 plus 1 is the number of orbitals. So there's 3 2p orbitals. We talked about those last week as being 2px, 2py, 2pz, 3 different m sub L values, but all 3 of these orbitals have the same energy. So in the 2p subshell, there's 3 orbitals you can fill, 6 possible electrons that can go in there, because you can get up to 2 electrons per orbital, but all 3 of those orbitals have exactly the same energy as each other. There's no difference there. So that's what we mean by degenerate orbitals, and that's something that will come up from time to time, particularly when we talk about putting electrons into individual orbitals, not just figuring out how many each subshell has. And that finally leads us into the approach that we're going to take, which is called the Aufbau principle. And the German flag here is because Aufbau is clearly a German word, which literally translates as building up. So the Aufbau principle is what we're going to follow when we decide how many electrons go into each subshell or each orbital within that subshell. And the way that it works is that I've kind of already described it. We're going to add electrons one at a time into whatever lowest subshell is available. We fill that subshell up, and then we go to the next one that's available and add electrons to that. And you just keep doing that until you've run out of electrons for whatever atom you're talking about. So electrons are added one at a time. The total number of electrons is determined by which atom you're talking about. But we're going to add those electrons one at a time to whatever the lowest energy subshell is that's available, that has an empty spot in it. All right, so using the concepts that we talked about, shielding, penetration, electron, all that gives us the ranking of the subshell energies from lowest to highest. And we'll talk about how we remember that from the periodic table in a little bit. And then we're just going to add electrons to the lowest energy subshell, fill that one up, and then if we have more electrons left, we go to the next subshell, and so on until we've added all of our electrons. Now what this gives us, when we follow this approach to determine the configuration, determine the population of each subshell, this gives us what's called the ground state electron configuration. We talked about what ground state means before. Ground state means the lowest energy state. So when you follow the Aufbau principle and add electrons into subshells in that way, you're going to generate what is the lowest possible energy arrangement of those electrons. So it would represent what's called the ground state. So let's define what this is. It's the arrangement of electrons into subshells, or sublevels as they're sometimes called, that has the lowest possible energy. So if you follow the Aufbau principle, and there is one other consideration that comes into play for determining the spins that we'll talk about as well, but if you follow the Aufbau principle for distributing electrons into subshells, that's going to give you the lowest possible energy arrangement. That's called the ground state configuration. So the way that we write this is that each sublevel that's populated, or each subshell, I'll use that terminology more commonly. So each subshell is going to be written as the following. It's going to be written as NL with some number subscript on it. where X is the number of electrons in this subshell. And if the subshell is empty, as will be the case for many of the higher energy ones, we just don't write it out at all. We don't have to write the 0 there. That would just imply that it's empty if it's not there at all. But for each one, each subshell that has electrons in it, you're going to write it in this way, where n is the first quantum number, the shell number. And then L is going to be written as a letter, typically S, P, D, or F. So the subshell designation for 1s, 2s, 2p, 3s, 3p, and so on, for each subshell that has electrons in it, and then a superscript X that tells you how many electrons are in that subshell. And that number can't be higher than the maximum number that goes in that subshell, as we talked about, but it may not get to that maximum depending on how many electrons you have. So that's how we're going to write out the configurations. We'll get a bunch of examples of this today and throughout the course, so we'll still use this concept. So we'll see what that looks like. All right, and so to be able to do this, then we have to know what order the subshells come in, which one is lowest energy, which one is next, and the ranking of them to be able to add electrons. And the nice thing is, in my opinion, one of the most beautiful things I'll teach you in this course is that the periodic table directly tells us the ordering of subshell energy. We don't have to memorize anything. Now, I don't know if your textbook still has it. A lot of people use this sort of like, I don't know if I can draw it properly, like this sort of, I don't remember how they do it. There's like I haven't used it in so long that I've totally forgotten. There's like this thing you can write where you write out 1s and then 2s, 2p, 3s, 3p, 3d, and you like draw these like diagonal lines through it and stuff. I'm not doing it right, so don't like copy that down, please. But there's diagrams like that you may have used before if you talked about this in high school chemistry, or your book might even still have it. But I don't like that because, as you just saw, like I can't do it anymore, and you might like clam up on a test and not be able to do it yourself if you need it. So my encouragement is to always use the periodic tables to tell you the ordering of the subshells. So to be able to do that, you just have to understand the ordering of the periodic table, how it's arranged, why does it have this shape that it has, and then when we go through and do electron configurations, you just step through the periodic table in numerical order until you get to the atom that you're interested in, and you just fill the subshells that you go through until you get to that atom. So let's try to talk about how that works here. So the way the periodic table is organized is that each row of the periodic table represents a different n value. 1, 2, 3, 4, 5, 6, 7. We'll talk about these bottom ones here in a little bit. Those are the ones that are cut out. These are cut out just so that the periodic table is not like way too long and unwieldy to deal with. They really belong right about here in this middle part here, like right where my pointer is now. That's where those ones are cut out of. So you might, if you draw the full periodic table, you could put it like that, but it would just be hard to read and hard to look at. All right, so that's the n values, and then the different columns on the periodic tables represent the different subshells that you would have. So these first two columns in the periodic table here, which I'll highlight in blue. The highlighter function on this program doesn't work as well, but you get the idea. And so those are going to be that's going to be the NS block of the periodic table. So as you go through the elements that are in this part of the periodic table, you're adding electrons into the S subshell. So 1s, 2s, 3s, and so on, but we always go in order. And then there's also one more over here. Helium is in a weird spot in the periodic table. It should be in the S block, but because it has chemical properties that are more similar to the ones below it here, it's put on the right side of the periodic table, but in reality it's still a 1s subshell that represented by helium. So don't be fooled by that one. That one's in a weird place. All right, what we also have then are going to be these blocks over here on the right side. And the direction that I'm highlighting has no significance. It's just for my writing convenience. This block here, except for helium, of course, this is our NP block. So as we go through those elements in numerical order, we would be then adding electrons to a P subshell. It starts at the second row, so 2p is the first the first P subshell. So this would be the 2p, 3p, 4p, and so on. All right. The middle part of the periodic table, which is my favorite, but we won't talk about a lot in this class, unfortunately, these 10 columns here that take up 3 full rows and then some man-made elements that take up this 4th row here. This periodic table is not even fully updated. I think there's like 118 now, but the man-made ones we don't really care about too much in this class or in general. All right, but this block here in the middle, this is the D subshells, but it's not ND, it's N minus 1D. So again, the N value comes from which row of the periodic table you're in. So here we're in the 4th row of the periodic table, but the first D subshell would be N minus 1, which is 3D. So this would be 3D, 4D, 5D. So the middle part is not given by the row that you're in, is N minus 1, the row minus 1. So 3D, 4D, 5D. All right, and the ones at the very bottom that are cut out from the middle, which we won't deal with a lot. We won't really do electron configurations for these elements because they're more complicated, but sometimes we have to pass through these to get to the one that we're interested in, so we have to still know them a little bit. So those two there are the F, that's where the F subshells would be arranged. So they're going to be N minus 2F. Now it's not obvious when they're placed down here where they came from the periodic table, but this first row comes from the 6th row of the periodic table, so it represents 4F, N minus 2 is 4. This one comes from the 7th row of the periodic table, it's cut out from right there, and so this would represent 5F. 7th row, N minus 2 is 5. So like I said, we're not going to do electron configurations for these elements, but for some of the elements here in the 5D block, we have to, or the 6P block, we have to step through those to get there. So we have to make sure we recognize that there is that intervening F subshell that's part of our configuration. Okay, so that's how the periodic table is organized, and like I said, what we're going to just do then is we're going to march through the periodic table in numerical order to get to the element we're interested in. As we go through each number in the periodic table, that's going to tell us, based on its location, which subshell gets filled as we step through there. All right, any questions on that so far? It'll make more sense, I think, when we use it, but that's something you're going to want to practice a lot and get used to, because this is the best way to do it instead of trying to memorize things. The last thing we need to be able to populate electrons into orbitals, so for doing electron configurations in terms of how many electrons are in each subshell, we just need the periodic table. That's enough for this. But if we want to start talking about how many electrons does each individual orbital have, because for example, the 3p or the 2p subshell has 1, 2, 3, 4, 5, 6 elements in it, which means it can have a maximum of 6 electrons. And there's 3 different orbitals in there that can hold those 6 electrons. So how many electrons are in each individual orbital, that you can't get from the periodic table alone. You have to use another rule, which is called Hund's rule. So Hund's rule is involved when you're filling degenerate orbitals, and especially when those degenerate orbitals are not completely filled up in that subshell. So when degenerate orbitals are filled, the way that we do it is we first put 1 electron into each orbital. And each electron that's in those orbitals has the same spin. So you'll do that first before pairing 2 electrons in the same orbital. So you have to singly fill each orbital first in the degenerate set of orbitals, and then you'll start pairing 2 electrons into the same orbital if you have more to put in. So you would still completely fill that subshell before moving on to the next one, but you would want to make sure that you put 1 electron in each orbital first before you start pairing up 2 electrons into the same orbital. And what you're doing here essentially is maximizing the number of unpaired electrons. Now, why this rule is important for determining the ground state configuration is because of pretty advanced quantum mechanical things called exchange energy. But long story short, if you have the more unpaired electrons you have in the same subshell, the lower the energy of that subshell will be. So you want to make sure you have the maximum number of unpaired electrons possible. So you start with putting 1 electron into each orbital, all with the same spin, before you start pairing them up. And so that's how Hund's rule would work in practice. The only time that it matters is when you have degenerate subshells that have more than 1 degenerate orbital present, which would just be not S, but P, D, and F. So everything but S orbitals would have this consideration. And again, the Y is kind of complicated and quantum mechanical, but for our purposes, we can say that it minimizes electron-electron repulsions. Because if you try to put two electrons into the same orbital, they're going to be closer together and repelling each other more strongly, versus putting those two electrons in two different orbitals, they're further apart, and that minimizes the repulsion. Now again, why they have to be the same spin is because of a thing called exchange energy that's beyond the scope of this course, but electron-electron repulsion is sort of at the heart of it. All right, so that's how Hund's rule works. So let's go ahead then and start populating orbitals and determining electron configurations. So there's sort of two layers to this that we might ask you to do. So one would be to just write out the electron configuration, which involves just telling us how many electrons are in each subshell. But then also we might give you diagrams in a Blackboard, likely a multiple choice question that asks you, well, what's the correct population of those orbitals, or what's the spin of the electrons and things like that, and that comes from Hund's rule that we just talked about. So let's do both of those for a few examples. So let's do boron and carbon, relatively simple. All right, so for boron we have Z equals 5. I should have the periodic table open, but I don't, so let me get that open for you real quick. All right, so boron is atomic number 5 here. Okay, so we're looking at this element here. Now the way that we figure out how many electrons are in each subshell is we have to go in numerical order up to number 5. So we start at number 1 here. So we have to remember that hydrogen is 1s, and so is helium. So that's going to be 1s1, 1s2. When we go to the second row of the periodic table, we're now in the 2s block here. So that's going to be 2s1, 2s2. And then to get to boron, this is the beginning of the 2p block. This right side of the periodic table is p block. We're in the second row, so it's going to be 2p1. We stop there because that's boron, that's what we're looking for. All right, so that's going to be the electron configuration for boron. We go through 1s for the first two elements, then 2s to get to atomic number 4, and then boron is the start of the 2p block, and there's only one electron in there to fill up the 5 electrons total. Again, that was from here that we just talked about. So 1s, 2, 2s2, 2p1 takes us to boron. All right, in terms of how we fill the orbitals, 1s and 2s both have 2 electrons in them, so they have to be filled. And remember, when the electrons are in the same orbital, they have to have the opposite spin. That's Pauli exclusion principle. So 1s is going to look like this. The up arrow indicates spin up, down arrow indicates spin down, or plus 1/2 and minus 1/2. Same for 2s. Now, in terms of 2p, one thing we need to recognize is that all 3 of these 2p orbitals are at the same energy. One of them is px, one of them is py, one of them is pz, although they're not explicitly labeled here. They're all at the same energy, and whether the electron is spin up or spin down is going to have the same energy as well. So there's actually a lot of different ways that you could write out that one electron in these 2p orbitals that are all equivalent to each other. So by convention, we go left to right, and we go spin up first. That'd be the most common way of doing it. But any of the other 5 possibilities would work as well and be a correct answer also. There's really 6 correct answers here for this particular one. So we could go like this. That's perfectly fine. Doesn't matter which of the p orbitals we fill. So we could go that. We could go that. Doesn't matter which of those 3 are filled with spin up. Or we could go spin down for any of the 3 possibilities as well. That, and that. So when you're putting one electron into a degenerate set of orbitals like this, it doesn't matter which orbital has the electron. It doesn't matter whether it's spin up or spin down. All of those are energetically equivalent. To keep things neat and organized, like I said, that's going to be the most common way. Put it in the first orbital with spin up, but you don't have to do it that way. And if you're doing a multiple choice question, you should recognize that all of those 6 possibilities that I drew, spin up in any of the 3 orbitals or spin down in any of the 3 orbitals, all of those are energetically equivalent and would be a valid way of indicating that population. All right, now let's go to carbon, which is just the next one over. I guess I'll use this periodic table since it's labeled. So carbon is here, number 6. It's kind of covered up by my highlighting, but that's where it is. So when we go to carbon, we do the same beginning point, 1s2, 2s2. Now we're in the 2p block, and we have to go 1, 2 over to get to carbon. So there are now 2 electrons in the 2p orbital. So there's just one more electron than boron. It's still in the 2p block of the periodic table, so we just add that second electron also into the 2p subshell. Okay, so for carbon it's very similar. 1s2, 2s2, 2p2. Now the only thing that's different with carbon though is when we fill the orbitals, we have to figure out what we do with the 2p because now we have 2 electrons in there and it's a little bit different situation. So 1s and 2s still look the same. But when we get to 2p2, remember that we have to follow Hund's rule. And what Hund's rule tells us is that we want to put 1 electron in each orbital and they need to be the same spin before we start pairing them up. So we would want to do something like this. Again, conventionally we work left to right, spin up first. But any combination where both electrons are in different orbitals with the same spin would be fine. So this one works, this one works, this one works, or all the spin down possibilities as well. It doesn't matter if they're both spin up or both spin down as long as they're the same as each other. So I know it's a little bit confusing to think that there's like all these different possibilities, but the key aspect is that the 2 electrons have to be in 2 different orbitals and they have to have the same spin as one another, both up or both down. So this here in the 2p is an example of Hund's rule. And Hund's rule didn't really matter for the first one because there's only 1 electron in that last subshell. So we didn't have to worry about arranging the spins, arranging the 2 different electrons. But here we have to worry about Hund's rule. And again, conventionally we fill left to right, spin up first, but there's a lot of other possibilities that are equivalent. All right, any questions on those relatively simple configurations? All right, now when we go to heavier elements on the periodic table, sometimes we'll use a shorthand approach for them because as we go through all the different elements, especially if we go to atomic numbers that are really high, you have to go through each subshell on the periodic table, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3D, whatever. So it gets kind of cumbersome to do every individual subshell like that. So the shorthand approach is, if we look at sodium here, let's do the full configuration first so we can see how the shorthand approach works. So for sodium, which is Na, right here, number 11, if we want to write the configuration, we start at the top, number 1, so that's 1s1, 1s2. Then we go to 2s, 2s1, 2p2. Then we go through 2p, 2p1, 2, 3, 4, 5, 6, completely filled. And then when we get to sodium, we're in the 3rd row back in the s block, so it'll be 3s1 for that last electron. So that would be the full configuration for sodium. 1s2, 2s2, 2p6, 3s1. Okay? So that's a valid way of writing it out, and you should be familiar with the full notation, especially in multiple choice questions it might be written this way. But there is a more convenient way of writing it. So what we can do is we can find which of these electrons are called core electrons, the ones that would belong to the nearest noble gas. Now we haven't talked exactly about what noble gases are, but just to give that away right now, this last column of the periodic table here is called the noble gases, and they have completely filled S and P subshells. You're always in 2p6 when you get to this column here, or 3p6, whatever row you're in. So what we can do then is we can find the noble gas that comes before an element. So sodium is number 11. The noble gas that comes before it, that's closest to it, is neon, Ne here. And we can abbreviate all of those first 10 electrons, 1s2, 2s2, 2p6, with just neon in brackets. So what we can say is that these first 10 electrons here, 1s2, 2s2, 2p6, that's the electron configuration of neon, the noble gas that's closest to sodium, that comes before it. And so what we can do is, instead of writing this out in full, we can just write that as neon in brackets. So if you see a noble gas in brackets, that's just abbreviating that you have all of those electrons for the noble gas plus whatever comes after it. In this case, it's just the 3s1. Okay? So neon 3s1 would be an alternative way of writing the configuration for sodium. The nearest noble gas which represents the inner or the core electrons are going to be indicated with brackets instead of written out in full. So if we just go 1 over from sodium to magnesium, Z equals 12 in the periodic table, we can save some time because instead of going through each individual subshell that leads up to it, we can just find the nearest noble gas first. I'll just use the one that's in the notes. Okay, so if we find magnesium right next to sodium here, the noble gas that comes before magnesium is also neon. So instead of doing all these different subshells that lead up to there, we can just write neon in brackets. We're at neon now. And then after neon, we go down to 3s, 3s1, 3s2. So a faster and shorter way of writing that would just be, okay, the first 10 electrons in magnesium all belong to neon configuration. After that, we had 3s2, and that's a perfectly valid way of writing that. So you'll see it both ways. You need to make sure you're familiar with both, either writing out the full expanded notation or the abbreviation with noble gas. Not that one is necessarily right or wrong, it's just that these abbreviated configurations are sometimes a little bit easier to deal with, especially for heavier elements that have larger atomic numbers. Another reason that this is important, in addition to potentially saving you time and just making it a little bit more concise to write out, is that it allows us to clearly define what the valence orbitals or valence electrons are. So these are another way of thinking about these are the outer electrons. And one thing that we'll see in this course as we start going forward into the next chapter, when we start talking about atoms bonding together to make chemical bonds, is that it's the valence electrons that are important for that. So whether we're forming ionic bonds or whether we're forming covalent bonds that are shared, all that stuff we're going to get to in the next chapter, it's only those outer electrons that participate in that. So it's really those are the ones that are most important for the chemistry. So when we abbreviate the configurations like this, everything that's in brackets is called a core electron. It's not one that we really care about as much in terms of the chemistry. Everything that comes after that would typically be a valence electron. So the main things we're going to deal with for valence electrons are the main group elements, which means that they're in the S or P block of the periodic table, either the first 2 columns or the last 6 columns. The transition elements are interesting in the middle, but we're not going to deal with them as much. But those that appear in the first 2 columns or the last 6, the S and P blocks, the valence electrons are the electrons with the highest principal quantum number. And again, that's the value of N. So for sodium, the highest principal quantum number is 3 for the 3s electrons. There'd be 1 valence electron, which is that 3s electron. For magnesium, there's 2 electrons that both have N equals 3, so there'd be 2 valence electrons that have N equals 3. So it's always going to be all of the electrons that are highest principal quantum number. So the s electrons and the p electrons that are in that highest principal quantum number. Here it's only s, but if we went to the p block, there would be s and p electrons with the highest value of N that would both count. So we'll give examples of that throughout this. All right. Now we're not going to do a lot with transition metals, but we do need to know how to figure out their electron configurations. And it's going to be the same approach as before. It's just that what we have to recall is that, and what's a little bit weird about this, is the NS subshell, it starts in the 4th row, so 4s or 5s or 6s for the transition metal. That's going to be filled before N-1d. So we don't always fill electrons in order of principal quantum number N. It turns out that once we get to the transition metal, we see that 4s comes before 3d, 5s comes before 4d, 6s comes before 5d. But again, if you know the organization of the periodic table, that comes directly from that. That's not something separate that you have to remember. But that is something that looks a little bit different about transition metals than the main group metals, where you're filling a higher value of N before a lower value of N in that part of the periodic table. But that won't really matter as long as you know the organization. Now, for the valence electrons for transition metals, probably not as much that we'll do with this, but at least you should know the definition. All of the s electrons in the outer subshell and all of the d electrons that are added last, so those with the highest N value, those are all counted as valence electrons. So basically it would be, in general, everything that comes after the noble gas, but as long as it's in the S or D subshell. So let's do a particularly difficult example, I would say, but the most difficult that you'll probably see in the transition series. Let's go all the way down to osmium OS. All right, so for osmium here, we'll stick with this abbreviated periodic table so you can see the subshells more clearly. Osmium is right here, number 76, OS. So let's figure out the configuration. Now, this one being such a high atomic number, it's going to be a lot easier for us if we go to the nearest noble gas first instead of doing all the core electrons. So before osmium, the nearest noble gas is xenon. So Xe in parentheses is going to represent the core electrons. But then after that, that's atomic number 54. This is 76. We still have like 22 more electrons to go. So we still have a lot more to add. So after 54, we come down here to 55, which is the 6th row of the periodic table. And we go through the S block first. So it's going to be 6s1, 6s2. And then we get a little bit weird because we go here to the 5D block, but we have to also jump down to 4F. So it's weird because 4F comes after the first 5D. So however you think about this, though, we're going to go 5D1, but then we're going to jump down here to 4F and go, because it's 57 down to 58. We go in numerical order. So that's going to be 4F 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. We go through all 14 of those. That takes us to 71. Then we jump back up to here to 72, which is still in the 5D. So that's going to be 5D 2, 3, 4, 5, 6. So we get all the way to 5d6. So basically to get from xenon to osmium, to get after all the core electrons, we go through 6s, we go through 4f, and we go 1, 2, 3, 4, 5, 6 over into the 5d, which means we have 5d6 as the last electrons we add. So that one's a particularly difficult one because it involves that 4f subshell being filled as well. So the core electrons we said were xenon. After xenon, we went through 6s. Technically speaking, if we go in numerical order, we go 5d1, then 4f14, and then 5 more in the d, but it's better to write this as just combining all the 5d electrons into one grouping. So 6s2, 4f14, 5d6. All right, so that's the order that we went in. S, then F, then D. To write it out. And then, other questions we could ask are how many valence electrons there are. So valence electrons are those that are in the S and D subshell that come after the core. So 2 of those, 6 of those, that's a total of 8 valence electrons. And if we want to write out the orbital population, we have xenon as the core, but then after that we have 6s2, 4f14. So the way we populate those is 1, 2, 3, 4, 5, 6, 7 individually filled first, but then we have to start pairing up because we have 14 total. So then we start pairing up 8, 9, 10, 11, 12, 13, 14. All of them are completely filled. And then to figure out the population of 5D, this is where we also have to use Hund's rule. So there's 6 electrons, 5 total orbitals, L equals 2, and the periodic table has 10 elements wide, so that's 10 total electrons or 5 orbitals possible. So for 5d6 we have 1, 2, 3, 4, 5, 6. So remember we do 1 electron per orbital first, and then we have to pair up because we have a 6th one that has to go in with one of the other ones. So that would be the correct arrangement of those. There's other ones that would be equivalent, but this is the most conventional one, and that would be 4 unpaired electrons. So the electrons that do not have a partner with the opposite spin in the same orbital, those are called unpaired. So this one, this one, this one, and this one, those 4 are all unpaired. Spin up, but no corresponding spin down electron next to it. So there's 4 unpaired electrons. So those are the most complicated ones for transition metals. The other 2 things that we expect you to know for the transition metals are 2 exceptions where using the periodic table to predict the electron configuration doesn't quite give it right. Turns out there's way more than 2 exceptions. This method of using the periodic table and getting the configuration is not perfect, and especially as you get to the lower parts of the periodic table, a lot of those subshell energies are really close together. The 6s and the 5d and the 4f that we talked about last time, all those are like really close in energy. So in terms of how the electrons arrange themselves, it's not always perfectly what you would predict from the periodic table. So there's a lot of exceptions, but only 2 that we expect you guys to know. So for any other one, just follow the approach that we're talking about today. But there's 2 that we want you to be aware of. So for chromium Cr, let's predict the electron configuration from this. All right, so Cr is one of the first 36 elements. We should know that that's called chromium, and that's right here, number 24. So the noble gas before that is argon. So we'd write argon as the core electrons. And then after that, this is number 18, we come down here. That's going to be 4s1, 4s2. Then we get to 3d, 1, 2, 3, 4, and stop at chromium. Okay? So our predicted configuration would have argon as the core, 4s2, 3d4. But this is one where we should know that this one is not quite correct. the actual configuration for chromium, what we do is we take one of these 4s electrons and bump it up to 3d. So still the same number of total electrons. We're not adding or subtracting electrons from this. It's still 24 total electrons. But one of the electrons from the 4s subshell gets bumped up to 3d, so that makes it 4s1, 3d5. Now the reason for this is complicated, and I'm going to give you sort of a half-baked, hand-waving explanation, which is that half-filled subshells are favored in this case. In particular, the D5 is a favorable one. So we have the option of going from D4 to D5 by just taking one electron up, and so that ends up being slightly better energetically. We don't really need to know the reasons for this, but you just need to know that this is an exception. And then the other one that has a similar outcome is copper. So the predicted configuration for copper, it's also in the 3D, so it has argon as the core electrons, just like chromium does. But if we find copper, which is over here, number 29, argon is the core, and then we have 4s2, 3d, 1, 2, 3, 4, 5, 6, 7, 8, 9. So our predicted electron configuration would end with 3d9 as the last electrons that we put in. So it'd be 4s2, 3d9, but the actual configuration, again, the prediction one here is wrong. We take one electron, just like we did for the other one electron from 4s, bump it up to 3d, and that gives us argon 4s1, 3d10. A completely filled d subshell is also favorable. So you just have to remember for these two, it's slightly favored to have either a half-filled subshell or a fully filled subshell for 3d, 3d5, or 3d10. So we take one electron from 4s to allow us to do that. We can't change the total number of electrons, but we can rearrange them slightly. And that's because 4s and 3d are really close together in energy, so it's not really a huge energetic penalty to do that, but you gain some energy by having either the half-filled or fully filled. All right, so any questions on those? Yep?
For the question above, where'd you get the 8 valence electrons from?
So for a transition metal, the valence electrons are going to be the s and d electrons that come after the core. So here it's going to be the 2 from 6s plus the 6 from 5d, a total of 8. All right, we have one more thing to cover, so any questions on that so far? All right, the last thing we're going to do quickly is just an overview then of the different categories of elements that we have in the periodic table. All right, and so the thing about electron configuration and why it's important is that a lot of the key properties of an element, especially its chemical properties, how it reacts with other things, the types of compounds that it makes, can be determined by its location on the periodic table, which is related to its valence electron configuration. So that allows us to sort of categorize elements based on their valence electron configurations. So the first division we need to understand is the division between metals and nonmetals. So there's this imaginary staircase that goes, it starts at boron and snakes down like this. And so everything to the left is going to be a metal. And then everything to the right of the staircase would be a nonmetal. And then there's some that are along the staircase that are on the borderline that are called metalloids. And so, but basically to the right we have the nonmetals. And I'll highlight those in blue here. So everything on the right side of the periodic table is a nonmetal. So that would include this whole column here, this whole column here, and then most of these, some of the ones right along the staircase, as we said, have a slightly different category, but all of those ones furthest to the right, away from the staircase, are all classified as nonmetals. Everything to the left is classified as a metal, except for some of the ones that are right along it. Okay. Now within the metals, though, on the left side, we have a few different categories of metals. So these first two columns here, which are, now hydrogen's not really a metal, so we'll just highlight those two columns, except for hydrogen. And then the metals that appear in the P block over here, so that would be starting with gallium and on down, tin on down, bismuth and polonium. Those are also metals. They're to the left of the staircase and classified as metals. And those ones are called main group metals. So if they occur in the S or the P block of the periodic table, they're called main group elements, and those that are metals are called main group metals. So those are going to all be highlighted in green here. And then in red, the other major categories of metals that we have are the ones here in the middle. So those in the D block of the periodic table, those are called the transition metals. As I said, one of the unfortunate things about general chemistry is you don't learn a lot about transition metals, but they're, for me, one of the most interesting. And then, running out of colors here, let's try purple. Down here, those are also metals, and those are called the inner transition metals, is how we call it, inner transition. And they have specific names, lanthanide and actinide, but I don't think we're going to have you guys worry about that. Then the last major category is going to be the ones on the borderline that I haven't highlighted yet. So boron, silicon, I need to get the highlighter. Boron, silicon, germanium, arsenic, antimony, tellurium. Sometimes you'll see slightly different lists of which ones are classified in this way, so don't worry about just know these 5 or 6 and you'll be fine. Those are called metalloids, the ones that are in between metals and nonmetals. They have some properties that are kind of like nonmetals, some that are kind of like metals, so they're in between. The one that I should have highlighted in green also is aluminum is a main group metal. So that one's also a main group metal. All right, but the ones that are in between, boron, silicon, germanium, arsenic, antimony, and tellurium, especially those first few, boron, silicon, germanium, arsenic, you should definitely know as metalloids. And then finally, the last thing we'll cover is that within some of these categories, you have subcategories. So we already talked about this column here is called noble gas. The column next to it here, the second to last column, are called the halogens. And then within the main group metals in the S block, we also have 2 categories. So we have the first one and the second one here have their own names. The first one is called the alkali metals. Hydrogen is not a metal, hydrogen is a non-metal. But all the rest in that column are alkali metals. And then the one up here, the second column, would be alkaline earth metals. So we do want you to be familiar with some of that terminology. We'll use some of that terminology throughout to describe elements. But this is the organization of the periodic table. It's related to electron configuration, and we will talk about some of the properties of a lot of these different classes of elements as we go through different parts of this course. All right, sorry for the disruption today, but we got through everything, and I'll see you guys a week from today.